Why do dictionaries raise key error rather than returning a sentinel value? And one of the things that I love about these questions is oftentimes somebody will look at them and they'll have a very superficial, a very facile answer. They'll say, well, what else would you do? But there are often a lot of different choices. In fact, if you think about other programming languages like JavaScript, when you go into a dictionary or in JavaScript an object and you ask for an attribute that doesn't exist, it doesn't raise an exception. It gives you an undefined, it gives you a sentinel value. Or if you're using C++ with a standard map, if you ask for a key and that key doesn't exist, it doesn't give you an exception. What it does is it uses the default constructor for that key. So why did Python choose key error? Let me show you a little bit what I mean, some of the specifics. Here we have a dictionary, and the dictionary is a mapping from English to characters that you might write in Chinese or in another language that uses characters. And we look up something in this dictionary, we look up the English word, and we get the corresponding, in this case, Chinese word, and we do something with it, we print it to the screen. I want to share with you a thought process behind what this all means, deeper than just, well, there's an exception that's raised and you have to be able to catch it. And I want to introduce to you a phraseology that's used when we talk about this problem, namely phraseology of in-band versus out-of-band encodings. And it's a much deeper idea than just coming to dictionaries. Let me share with you what I mean by that. And the canonical example that I use for in-band versus out-of-band encodings is not Python related. It's actually something that you've all seen before. If I have a set of files on disk, let's say in some temporary directory, and those files are named A, B, C, D, E, and there's 4 files, and you can see these 4 files here, A, B, C, and D, E. And I use a program like find to find these files, so I can see files A, B, C, and D, E. And I can take those files and I can pipe them to a program like xargs to figure out, I don't know, how much disk space they use. They're empty files, so they should all use 0 disk space. I get an error here. It figures out that C has no space allocated to it, A and B have no space, but it errors when looking at this DE file. And the reason for that is the find command gives you the file names, new line separated. The xarg command takes those file names, new line separated, or actually space separated. It doesn't distinguish between new lines and individual spaces, and so the xargs command ends up passing to my du command. Something looks like this. And even if I make this pass them one at a time, you'll see it doesn't have the ability to disambiguate between is D space E 2 files or 1 file with a space in it. This is an in-band, out-of-band encoding problem. Let's break down the vocabulary a little bit. When we talk about an in-band encoding, what we're talking about is 2 channels or multiple channels, and using the same channel for metadata and data, or using the same channel for data and control. That's usually what we mean. And so when we talk about an out-of-band encoding, what we're talking about is using the same channel or using different channels for metadata and data, or using different channels for data and control. And I'll show you why this applies to our disk use problem. When we're using the command line, the only way that we can transmit information from one program to another program is by piping. And typically we don't pipe on multiple streams simultaneously, so we're all piping on the same stream, the same channel, standard out. Well, that standard out channel has 2 responsibilities: giving the names of the file and delimiting where one file name begins and the next one ends. You're using the same channel for encoding both the data and the structure, the data and the metadata. And when you have an in-band encoding, there's always the risk of ambiguity. You can't tell, was this data or structure? Was this data or metadata? Was this data or control? And so when you have in-band encodings, there's about 3 separate approaches that you can take in order to solve this problem. The first approach you can take is what you might call partitioning. You take the space of all the possible entities that can exist and you partition them in a way, and you say these correspond to only data entities, these correspond only to metadata entities. And I'll give you an example of that. For the command line case, what you can do is you can partition the space of these names of files, because we know definitively that a file name on Linux or any POSIX-compatible operating system cannot have a null byte, what we can do is we can have find give us these delimited by a null byte, because we know it can never be part of a file name. And then we can have xargs split on null bytes, and we no longer have this ambiguity. You can see it correctly passes everything around, and it works correctly. And so the idea of partitioning is you take the entire space and you break it into parts, and you say these parts are unambiguously always data, these parts are unambiguously always metadata. This occurs in other fields. Think about this. In a pandas data frame, if you have nan values, well, one of the problems is historically you can't encode this missing data knowledge in an integer array. Because in an integer array, what particular value represents missing? In the financial field, a negative value for something like a stock price, okay, sure, you partition the space. Positive values are actual stock prices, but a stock price can't be negative. So negative values indicate different error circumstances. But the partitioning problem is a huge problem when there may not be an easy way to partition and say these are explicitly always data or these are explicitly always metadata. The other approach you can take is some kind of escaping approach. So you have some additional control character, and that control character says the next things there are going to be metadata. But the problem with that is escaping oftentimes relies on partitioning, because you have to escape the thing that introduces that character. And XML has this big problem, because in XML, the way that you notate raw data is with that CData block. But what happens if you have the exact string for CData within the CData block? And so when you see this desire to do sort of escaping, or quoting is another way people do this, you often see that rather than partition with a single unique partitioning, people have customizable partitioning. For example, when you're using the command line, when you're using something like bash and you want to have like a here doc, you do something like this. You say, mark the end of the document with this string, and here's where the end of the document is. And here is where you put your bash string. Well, the thing is, you're guaranteed that you don't have to partition this space, because if EOF appeared somewhere in the middle of this thing, you would just change what your escaping or quoting character is to something else. And so what you see is for escaping or quoting to not need partitioning, well, typically what we end up having to do is we end up having to have some sort of customized escaping or quoting where you decide based off of what your knowledge of the data is what that escape or quoting character is. And so you have these different mechanisms for avoiding the ambiguities in in-band encodings. Partitioning, escaping, and quoting are two of the major ways. Let's talk about out-of-band encodings, though. Now, the out-of-band encoding idea is, well, let's just use a different channel or a different way to represent this data. And that's exactly what's happening when you have a dictionary and you look up a key that doesn't exist. Because think about this. When you have some dictionary in Python and you do something like this, if this gave you a value, like a dummy value or a sentinel value, how could you guarantee that that couldn't be the actual underlying value of that dictionary? You can't, right? Because if you said, oh, if the key doesn't exist, return a none. Well, what if there is a none there? And shell explicitly has this problem because if you're a Z shell user like I am, you may know that Z shell actually has associative arrays very similar to our Python dictionaries. And in these associative arrays, we can have key value mappings like A to 1, B to 2, and C to 3. And we can look things up and we can say, okay, give me what the array has at A, or give me what the array has at C, or give me what the array has at D, but here they give you an empty string. What if there wasn't actually an empty string in here? You couldn't determine, did this thing belong to the associative array? Was there an entry at all, and it happened to be an empty string, or wasn't there an entry? And this is a serious problem, and you know what? The Stack Overflow question for answering how do I determine whether a key is in an associative array in Bash or Z shell is 100% completely wrong because it doesn't account for this. Well, we would have exactly that problem in Python if we return some sort of sentinel value, because how can we say that sentinel value is guaranteed to not be an actual value there? Well, if you use the in-band encoding approach, you actually see people do this sometimes. What they'll do is they'll say something like missing equals object, d.get for some key, missing, and then they say if this thing is missing. And you can see this is just the kind of escaping, quoting, partitioning scenario where you're custom defining what the missing object is, because you know this thing probably can't appear in this dictionary because you only created on this line. Now, I don't think that's strictly correct either, because this dictionary could be some dictionary-like structure that could be mapping to all the objects that are under the garbage collector within your interpreter. And so this thing could have found its way into D if D happened to be live looking up, the linked list of all the garbage collectible objects. Very unlikely scenario, but maybe it might show up in some narrow cases. We all are experts after all. Instead, what the Python dictionary chooses to do is it chooses to use an out-of-band encoding. It chooses to use an unambiguous approach to return or to signal that an error occurred that is distinct from the channel that's used for returning data. And if you think about this more generally, you can think exceptions versus return values are an out-of-band encoding. An exception tells you, without any ambiguity, the thing that's happening here is an error that could not be potential data, as opposed to sentinel values where there could be some ambiguity there. And if you think about like searches, it's often the case that a search might raise a key error or an index error, a not found error. Well, searches also sometimes return none. If that search parameter is intended to return like a numerical value, representing, say, an index where something occurred, oftentimes it'll return a 0. Actually, no, it couldn't return a 0 because it could be the 0th element, so it'll return a -1. That's kind of clumsy. Or return a none value. But fundamentally, you can see the dictionary raises this key error because it wants to give you an unambiguous way to determine that the key wasn't there, where all of these other approaches with the in-band encoding have necessary ambiguities and require some strategy for eliminating that ambiguity. There are more strategies than partitioning, escaping, and quoting. But rather than talk about that, I want to talk about one more small thing, and then I'll show you why this all matters. The other reason why the Python dictionary raises a key error is it is not guaranteed that the result of this operation of looking this thing up and failing to look it up can allow the program to continue running. Let me show you what I mean. Here, if we have the value 1 and we look it up, everything's fine. If we look up the value 4, if we look up the corresponding value for the key 4, this blows up. We can tell this dictionary, do a .get operation. And when we tell this dictionary to do a .get operation, it basically returns this sentinel value that we've selected. If we don't specify a sentinel value, it'll use a none value by default. But note, this program is wrong. Just because this program terminated, just because it ran to completion, doesn't mean that it ran correctly. Because to write 4 on currency using a CJK script, you don't write NONE. This is meaningless. This is nonsense. This program ran to conclusion and gave you absolutely useless information. And if you happen to try to do something with this value, like do a centering of this, because you assume, this is going to give me a string back. I'm mapping strings to strings. This fails as well because you can't do something with this value. In fact, what you can see here is the problem with returning a sentinel value is not just the ambiguity, but it is very easy to hide errors. The error actually occurred on this line. There is no meaningful way for this program to continue running in the absence of that mapping. You cannot tell me how to translate this if you have never heard of the original word in the first place. And yet, the program ran to this point and gave garbage output, and then it failed on this point. We took an error that occurred here, and we just pushed it down to this line, which is strictly worse than signaling the error when the error actually occurred. This is why I would say the use of .get is probably a sign that maybe you need to think about whether that lookup is allowed to fail or not, and whether you have a meaningful default, because in the absence of a meaningful default, you might not be any better off than just raising that key error and terminating. In fact, I think the correct behavior of this program is the moment the lookup fails, terminate, because there's nothing you can meaningfully do to continue running this program once that fails, and anything you're going to try to do is just going to be passing the buck, is just going to be making somebody else's life harder. If you make this an empty string, sure, the program runs to completion, but the output is total garbage. And until somebody looks at that output, they're not going to see that it's total garbage. And guess what? This is exactly what happens in JavaScript, because I know every single one of you have gone to some dodgy JavaScript page and you've seen an error pop up. Undefined is not an object, or undefined doesn't have such and such method. And you're like, I don't know what's going on here. And you click through that a couple times and suddenly the page appears to continue working. Probably what happened is somebody tried to do the equivalent of a lookup on a JavaScript object. The lookup failed. It gave undefined. That undefined wasn't immediately used, and so it percolated from one stage of the program to the next, to the next, to the next, and then suddenly somebody tried to do something with it, and it blew up in their face, and it should have signaled the error all the way at the front, because the reason you're seeing it is the authors of that web page could not track down where the error originally occurred because they created that distance between the lookup failing here and then it being used many, many thousands of lines of code later. And this is likely why those errors persist. And so the Python dictionary chooses to do this for your benefit. Signal the error as soon as possible right up front. However, it is the case that we know that there are certain mappings, certain lookups, where there are meaningful defaults. For example, if we had a grocery list, and the grocery list contained things that we bought at the store, like we bought some watermelon, and we bought some orange juice, and we bought some bread. If you asked me, well, how much peanut butter did you buy? There's a meaningful default. I bought 0 peanut butter. And so this is the case where the .get would be totally meaningful with a very meaningful default of 0. Anything that's not in this mapping is guaranteed to be a 0. And this is very similar to the C++ standard map. Rather than doing the .get here, a very common thing you might do is use a collections.default dictionary. But my guidance for the use of the collections.default dictionary is there a meaningful default where if a mapping doesn't exist, you can supply a default and the program can continue running and give reasonable output. If there isn't, don't use this. Let the key error happen and handle that explicitly. Otherwise, use a default dictionary and you have some easy syntax. There you go. And in this case, this probably should be a collections.counter, a specialization further than the default dictionary, but there you go. For each one of these questions, I also want to share with you a little bit of why this all matters in the first place. And I want to share with you where this in-band, out-of-band encoding is a much broader idea than just looking up keys in a dictionary. Because some of you have used the pandas data frame. And when you used the pandas data frame, you might have accessed a column by using the dotted access or the square bracket access. And you might not have had a good sense for why do I use one or the other. Now, obviously, the dotted access for getting a column from a pandas data frame will not work if that column happens to have a space in its name, because it's no longer a valid Python attribute. But the getAttr access will work perfectly because it's a valid key. Think about this. What if that column happened to be named something like info? Well, there's an ambiguity here because df.info is a function that exists on a pandas data frame. And what you can see here is we've taken, with this dotted access, all of the different attributes and mechanisms that we can perform on a pandas data frame, and we've conflated them in the same namespace as all of the data that's contained within. In other words, we're using the same channel, the attribute access, to store both the mechanical structural things we can do to the data frame and the information about the data that it contains, the column names. And there's an ambiguity. This is why I always use the square bracket access, because it's unambiguous. The square bracket access always means give me a column. It's an out-of-band encoding of the idea of looking up a column that can never be confused with, oh, .info, maybe .info is the bound method that tells you information about your data frame. And this ambiguity around in-band and out-of-band encoding is also something that comes up quite a bit in API design. Because anytime you're designing an API, you really have to think, this thing that I'm using to represent metadata, am I guaranteed that it's metadata, or could it be confused for data? For example, in the design of tools like Xarray's data array, here you have a data array that represents maybe some image with pixel values from 0 to 255. And one of the things you can do with this is you can do selections. So select all of the slices of this image where the X value is 0 or 5. And you can do this with interpolation as well. So you can say, select all the points in this image at 0, 5, and 7, all those slices of that image, and linearly interpolate. The original data has X values of 0, 5, and 10. In order to control the interpolation method, whether it's linear or nearest or whatnot, you pass a method parameter. But notice, we are using the keyword arguments here to denote the mechanisms, the metadata, the modalities for how this interp works, and the data, the columns that it's going to look things up on, or in the case of Xarray, the coordinates, the dimensions that it's going to look it up on. Which means, if it were the case that this that this coordinate was not called x, but was called method. It turns out that in X-array, we do not have the ability to do the dot cell lookup if we happen to have a dimension called method, because then it would be ambiguous with the keyword argument named method. This is a huge API mistake, and these kind of API mistakes are everywhere. And so why this matters is anytime you look at taking two distinct things and conflating them in the same mechanism, modalities and data and structure, data and metadata, data and control, think about it in terms of an in-band or an out-of-band encoding. In-band encodings are okay if you can do those unambiguously, and key ways you can do those unambiguously is because you can partition the space or because you can find some sort of escaping mechanism. Otherwise, an out-of-band encoding is likely to be strictly correct and significantly less error-prone than the in-band encoding. That's why it matters.